Chemistry of a block element by Dr. Anita A. Ghare, MSc PhD, Assistant Professor in Chemistry, Dattajirao Kadam Arts, Science and Commerce College, Ichalkaranji. This is periodic table, long form of the periodic table, and here this periodic table is divided into 4 blocks depending upon the orbital in which last electron enter. Here the first 2 rows, they are S block element. Group number 13 to 18, these are P block element. Group number 3 to 12, they are D block element, and this is the at the bottom there is A block element. We can see here this is S block, P block, D block and A block element. A block element, D block element is known as transition element and A block element is known as inner transition element. The position of D block element is here actually, but for the sake of convenience it is shown at the bottom of the periodic table. They are subset of 6th and 7th period. There are 2 series of the A block element, elements whose F orbital getting filled by electrons, they are called A block element. A block element have electrons 1 to 14 in the F orbital. D orbital is the penultimate shell and S orbital is the outermost shell. So generally electronic configuration of F orbital is n-2 F 0 to 14, n-1 D 0 to 1, ns2. There are 2 series in the A block element corresponding to the filling of 4f and 5f orbital. The elements of 4f series, they are from cerium to lutetium, and the elements of 5f series, they are from thorium to lawrencium. The first series of elements where 4f orbital is in the process of filling, they are known as lanthanides, and the atomic number, it is including from 57 to 71. All these elements are non-radioactive except promethium, which is radioactive. So general electronic configuration of lanthanide elements is 4f 0 to 14, 5d 0 to 1, 6s2. The second series of elements are called actinide elements, and they include the elements from atomic number 89 to 103. They are all radioactive nature, and general electronic configuration of actinide is 5f 0 to 14, 6d 0 to 1, 7s2. So these are 5f elements which are actinides. This is about the occurrence of the actinides, about the occurrence of the lanthanides. Lanthanides are reactive elements, so they never occur in free state. They always occur in combined state in the form of silicate, phosphate, halides, carbonates. Silicates and phosphates are more plentiful, and as per the Harkin's rule, lanthanides having odd atomic number, they are less abundant than those having even atomic number. Now these are the minerals of lanthanide element from which we can extract the metal. The important minerals are bastenicite, monazite, xenotime, etc. and their chemical formula, and the content is high, and these elements, they occur in China, USA, Australia, former Soviet Union, Africa, Malaysia, etc. Now this is the general electronic configuration. As we have already seen, A block elements general electronic configuration n-2f 1 to 14, n-1 d 0 to 1 and ns2. For lanthanides, it is 4f 0 to 14, 5d 0 to 1, 6s2. If we see the electronic configuration of lanthanides, then all the lanthanides have 6s2 common, but the variable occupancy of 4f and 5d subcell. Lanthanum itself does not possess any 4f electron, but it is included in the lanthanides as it is showing close resemblance resemblance with all the remaining lanthanide elements. For lanthanide element, the general symbol Ln is oftenly used. The electronic configuration of elements with fully filled, that is F14, and half filled F7 orbitals are relatively more stable, and this extra stability of half filled orbital is shown in europium and gadolinium. The element yttrium with fully filled d orbital with the electronic configuration 4f14 6s2, it is also stable due to extra stability associated with a fully filled configuration. Except lanthanum, the elements gadolinium and lutetium have single electron in 5d orbital, but the remaining lanthanides do not have electron in the 5d orbital. We can see here the lanthanide elements from lanthanum to lutetium, atomic number 57 to 71. This is expected electronic configuration. Xenon core 4f0 5d1 6s2. Here this is expected electronic configuration, but observed electronic configuration, it is somewhat different. And if you see observed electronic configuration, here only lanthanum, then gadolinium and lutetium, these three elements, they are having one electron in 5d orbital, and others are not having electron in 5d orbital. All are differing in the number of 4f electrons. Oxidation state. Common oxidation state for lanthanide is +3 and it is more stable. Loss of 2 6s electron and 1 electron from 5d or 4f gives +3 oxidation state to lanthanide. Some elements, they are showing +2 or +4 oxidation state. The examples are lanthanum, promethium, holmium, erbium, lutetium show +3 oxidation state. Cerium, praseodymium, neodymium, they are showing +4, and samarium, europium, thulium and ytterbium, they are showing +2 oxidation state. So predominantly there is +3 oxidation state. +3 oxidation state in lanthanum, gadolinium and lutetium, it is due to extra stability associated with f orbitals or f shell electronic configuration. The cerium and terbium, it shows +4 oxidation state, and here cerium +4, it is having 4f0, and terbium +4, it is having 4f7. Occasionally +2 and +4 ions, they exist in solution state and sometimes in solid state. This irregularity, this +2 and +4 oxidation state, they are anomalous oxidation state, and this irregularity arises due to extra stability of empty half-filled and filled F subcell. So here we can see the lanthanum +3 electronic configuration. These are the lanthanum electronic configuration. There is loss of 2 electrons from 6s and 1 electron from 5d or 4f. So we can have here the electronic configuration for lanthanum +3 ion. Stability of anomalous oxidation state +2 and +3. It can be explained on the basis of extra stability of empty, half-filled and completely filled 4f subcell. Cerium shows +4 oxidation state because it is having electronic configuration 4f0, 5d0, 6d0. Now this cerium +4 oxidation state, it is stable due to this empty 4f subcell. Europium +2 and terbium +2. This their electronic configuration is 4f7, 5d0, 6d0, and these two europium +2 and terbium +2, these two oxidation states, they are stable because extra stability is associated with this half-filled F subcell. Then ytterbium +2 and lutetium +2. These two ytterbium plus 2 and lutetium plus 3. These two are stable due to completely filled F subcell, that is electronic configuration 4F14, 5D0, 6D0. Not only this, but some lanthanides also show stable oxidation state, that is +4 and +2, though they are not having completely filled, half filled or empty F subcell. For example, promethium +4. Here, this oxidation state, it is stable, though it is not having 4F0, 4F7, 4F14 configuration. We can see here the electronic configuration is 4F1, 5D0, 6D0. Similarly, neodymium +4. Here also no half filled, completely filled or empty F subcell. Samarium +2. Here also we can see 4F6, 5D0, 6D0 configuration. So stability of this oxidation state, it is not decided by extra stability due to completely filled, empty and half filled F subcell, but some other factors are responsible for that. Now the most stable oxidation state of lanthanide is +3. So ions in +2 state and +4 state, they are less stable. Ions in +2 oxidation state, they tend to change +3 oxidation state by loss of electron, and they are acting as a reducing agent. Whereas the ions in +4 oxidation state tend to charge +3 oxidation state by gain of electron, and therefore they are acting as a good oxidizing agent in aqueous solution. So here oxidation state +2, +4 less stable, and +2 oxidation state ions act as a reducing agent, and +4 oxidation state ions acts as a oxidizing agent. Now about the trend, atomic and ionic radii trend in group and period. Now as we know, down the group, number of electronic shells goes on increasing, and as number of electronic shells goes on increasing, the valency electrons held less strongly to the nucleus, and because of that we can see atomic radius increases. So this trend is observed in atomic and ionic radii down the group. Atomic and ionic radii in a period we can see that the number of shells remains as it is. Two cells are here, we can see number of cells remains same, electrons are added in same cell, so there is no addition of extra shell, and as the atomic number increases, the nuclear charge increases, and this increased nuclear charge pull the electrons inward, so atomic size decreases. So this is the general trend in atomic and ionic radii in group and in period. Here we can see same trend in lanthanides also. So we observe the lanthanide contraction. Now what is lanthanide contraction? The gradual decrease in atomic and ionic size of lanthanides with increase in atomic number is called lanthanide contraction. Now what are the causes of lanthanide contraction? As atomic number increases, the positive charge also increases. Positive charge means here number of protons increases. As atomic number increases, other things decreases, that is atomic radius and ionic radius decreases, and screening effect, it is also decreasing. The causes are all the 14 incoming electrons, they are added in the same subcell, that is 4F subcell from lanthanum to lutetium. The 4F subcell is an inner subcell, and its distance from nucleus is much less as compared to 6 cell. As atomic number increases, nuclear charge increases, that is number of proton increases by 1 unit at each element, and we know that the shielding effect of 4F electron, it is very poor. Now we can see here, this is the outermost cell, that is NS orbital, that is valency cell. This is the 5D orbital, that is penultimate shell, and this is 4F orbital, n minus 2f orbital. It is anti-penultimate shell. Now we can see here this anti-penultimate shell, it is close to nucleus. Anti-penultimate shell is close to nucleus, that is 4f subshell is close to nucleus, and it is away from the valency shell. So because of that, there is a shielding effect is not working, and attraction increases because of this decreased distance of 4f shell from the nucleus, and because of that the size electrons, they are pulled inward and size goes on decreasing. We observe the lanthanide contraction. Now if you see the trend in atomic and ionic radii for lanthanide element from lanthanum to lutetium, we can see here lanthanum atomic radius 169, 165, 165, 164. Some anomalies they are observed, but overall there is decrease in atomic radius. Also we can see there is decrease in ionic radius from 106 to 85 picometer for M plus 3 ion. So this is known as lanthanide contraction. Now what are the effects of lanthanide contraction? There is very small decrease, but gradual decrease, but because of that decrease or lanthanide contraction, there is decrease in basicity. Larger the size of cation, greater is the tendency of such hydroxide to dissociate, and stronger will be the base. So this is the first effect or first consequences. Then ionic radii of post lanthanides. The element which follow the lanthanides in third transition series, they are known as post lanthanide elements. The ionic radii of the element which follow lanthanum, they are similar to that of the elements of previous period. Generally we can see that here we can see that in S block elements the size goes on increasing, but here for post lanthanides element we can see there is no increase in the size, and this is the effect of lanthanide contraction on post lanthanide elements. These are the post lanthanide elements. Here we can say hafnium, from hafnium onwards. So these are post lanthanide elements. Here what is expected, if you see the scandium, that is first transition series element, its radii is 160, yttrium 180, lanthanum 195. So we are observing the increase here, but due to lanthanide contraction, see the effect here on the post lanthanide elements, and they are having similar atomic and ionic radii. Now because of that, here one more point is that lanthanides, they show similar chemical properties. As they are showing similar chemical property, they occur together and they are difficult to separate. The properties of ion depend on its size to charge ratio, that is charge to radius ratio. Lanthanum plus 3 ions, they have same charge, but there is very small differences in the ionic radii of lanthanide. So all of them show similar properties. So this is also an effect of lanthanide contraction. Here we can see there is presence of chemical twins. These chemical twins, they are having similar number of valency, and they are having similar properties. They are known as chemical twins. So here zirconium hafnium, niobium tantalum, molybdenum tungsten, technetium rhenium, these are chemical twins. And as lanthanides, they are showing similar chemical properties, they are occurring together and difficult to separate. This is also one more impact or consequence of lanthanide contraction. Densities of element of third transition series from hafnium to mercury are almost double than those of the elements of second transition series. We can see here see, these are the first transition series from scandium to zinc, then yttrium to cadmium, and lanthanum to mercury. So these are third transition series. Now here these are the density values. Density values. Now when we move from first transition series to second transition series, say there is small increase. But if you see here, zirconium, hafnium, niobium, tantalum, molybdenum, tungsten, here we can see that the densities are almost double. Densities are almost double, and this is the effect of lanthanide contraction. Thank you very much for watching this video. Thank you.